than 2 centuries ago, the origin of stars remained a subject shrouded in myth and mystery. Many people at the time believed humanity would never uncover the truth. But the development of spectroscopy and atomic physics in the 19th and 20th centuries laid the foundation for uncovering the structure of stars as well as the diversity of the universe, something astronomers of the past could only dream of. It's astonishing that the most common chemical elements on Earth, such as oxygen in the air, carbon in living organisms, or silicon in rocks, make up only an incredibly tiny fraction of the universe. Throughout the universe, hydrogen is the most abundant chemical element, far surpassing all others. By mass, hydrogen makes up about 74% of all elemental matter in the cosmos. The helium element makes up 24%, while all other chemical elements combined account for only 2%. So how do astronomers determine these numbers and uncover the composition inside stars? To understand this, we first need to briefly explore the atom. In 1869, when Russian chemist Dmitry Mendeleev arranged the chemical elements into the famous periodic table, showcasing their similarities and differences, no one could yet explain what gave those elements their distinctive chemical properties. It wasn't until after 1911 that this question was answered when Ernest Rutherford and his team of physicists at the Cavendish Laboratory of the University of Cambridge discovered the structure of the atom. Rutherford discovered that the atom has a nucleus, which contains most of its mass and carries a positive charge. He compared the atomic nucleus to the nose in London's Amber Theatre. Today, many people often liken an atom to a fly in a cathedral. This comparison implies that an atom is mostly empty space, with the majority of its mass concentrated in an extremely tiny central region. The key to determining most of the chemical properties of an atom lies in its nuclear structure. Within it, there are extremely tiny subatomic particles called protons. Each particle is extremely small in size, with a diameter of just 1/1,000,000th of a micrometer and carries a positive charge. The number of protons determines the chemical reactions of the atom. For example, the nucleus of a hydrogen atom contains only 1 proton, making it the simplest type of nucleus. An oxygen atom has 8 protons, a carbon atom has 16 protons, and other elements in the periodic table follow a similar pattern. Since protons carry a positive charge, they tend to repel each other. To prevent protons from repelling each other and flying apart indefinitely, nature created another type of particle to act as a binding agent, the neutron. These atomic particles have properties similar to protons but are electrically neutral. Neutrons cannot exist independently outside the atomic nucleus for long periods. When isolated, they decay on their own after about 15 minutes. However, within the atomic nucleus, protons remain stable and tightly bound together. The more protons a nucleus contains, the more neutrons are needed to maintain balance. For example, the atom with the second simplest structure is helium, consisting of 2 protons and 2 neutrons, while lithium has 3 protons and 4 neutrons. Unlike protons, which determine the chemical properties of an element, even if the number of neutrons changes, the element retains its fundamental chemical nature. The different forms of this element are called isotopes, some of which may be radioactive. Typically, a heteroatom contains only 1 proton and no neutrons, but there is also another type of heteroatom that includes a neutron. This heavy isotope of hydrogen is called deuterium. Due to differences in the number of protons and neutrons in their atomic structure, natural isotopes will have different atomic masses. The lightest element is hydrogen, while the heaviest naturally occurring element on Earth is uranium with 92 protons and 146 neutrons. The difference in atomic mass among elements is the key factor that creates Earth's unique chemical properties. Our tiny planet doesn't have enough gravitational force to retain the lightest elements like hydrogen and helium. Mercury, Venus, Mars, and the moons are merely tiny dots in the solar system, all too small to retain an atmosphere. Only when a planet reaches a mass equivalent to that of Jupiter or Saturn, about 300 times the mass of Earth, does its gravity become strong enough to retain all elements. Although neutrons can stabilize the atomic nucleus, they cannot neutralize the charge of protons. The atomic nucleus always carries a positive charge by nature. This charge is typically balanced by negatively charged electrons, tiny particles that orbit around the nucleus. If a nucleus contains 10 protons, there will be 10 electrons moving around it, ensuring the atom remains electrically neutral. Going back to the initial comparison, electrons are like tiny dust particles covering the entire cathedral, floating around the flies. Electrons in an atom can absorb energy when the atom is excited, thereby transitioning to a higher energy orbit. At this moment, the atom is in an excited state. The electrons will quickly return to a lower energy orbit, allowing the atom to stabilize again and release energy in the process. An atom can lose electrons if it absorbs enough energy, causing the electrons to be completely ejected and the atom to become a positive ion. This process is called ionization. The atom will quickly attract other negatively charged electrons to fill the vacancy, while releasing energy as the electron moves into the orbital. It may sound unbelievable, but this very property of electrons has become the ideal tool for astronomers to explore the compositional structure of celestial bodies. In 1830, French philosopher Auguste Comte published his work Cours de philosophie positive, translated as Course in Positive Philosophy *. This book offers a very noteworthy and entirely reasonable observation within the context of that time. Comte asserted that humans would never be able to understand the composition of the Sun, as it is too distant. Even if touched, this also holds true for other celestial bodies. Except for one special case under this rule, which is meteorites occasionally falling from space to Earth. Something humans can collect for study. They often had a self-destructive structure, leading people at the time to believe that metal might be an extremely abundant element in the universe. Just 3 years after Comte's death, in 1857, two German scientists, Gustav Kottrup and Robert Bulson, discovered a method that made studying distant celestial bodies much easier. This is like a dream come true, opening the door to exploring the universe in a completely novel way, never before imagined. They studied a strange phenomenon. When sunlight passes through a prism, it splits into basic colors, called a spectrum. The dark lines running vertically across the spectrum resemble a series of barcodes overlaid on a vibrant rainbow. Scientists also discovered that if a sample of a pure element is burned, the flame will produce a distinct characteristic color. For example, sodium flame is orange, while lithium flame has a purple-red hue. When light passes through a prism, it splits into multiple colored bands, with the brightest band resembling the color observed during combustion. Even with certain elements, they only produce a single colored line. What is the relationship between the dark lines in a continuous spectrum and the bright lines observed when burning a sample in a flame? Chope began researching how to use the new burner lamp invented by Bunsen. He conducted the burning of chemicals, analyzed the refracted light through a prism, then meticulously studied sunlight. Finally, it was realized that elements only absorb the same wavelengths of light as those they can emit. In reality, they store the absorbed light energy briefly before emitting it all around as light. For example, Natri can emit and absorb yellow light with a wavelength of 589 nanometers. Litri is red with a wavelength of 670 nanometers. With knowledge of atomic structure and electron energy levels developed since the early 20th century, this can be fully explained. However, the structure at that time was limited to research and had not yet explained the reason why elements emit their characteristic spectra. Each element possesses a characteristic wavelength, much like a unique fingerprint. Their ability to emit or absorb light depends entirely on their current physical state. A glowing stream of hot vapor, such as that produced by burning an element in an experiment, will emit light characteristic of that specific element. But a hotter stream of gas emitted from behind will absorb its characteristic radiation, forming dark lines in the light spectrum. Astronomers quickly realized that the Sun's surface is an extremely intense light source, enveloped by an atmosphere of more rarefied gases. The work of the spectroscope plays a crucial role in studying the chemical composition of the Sun as well as distant celestial objects beyond its reach. Scientists simply need to gather enough light, then pass it through a prism or a spectroscope to separate the light into its components. From there, they can measure the wavelengths of the dark lines that appear in the spectrum. The chemical composition of the universe suddenly became clear before their eyes. The first spectroscopic studies revealed that stars appeared to be primarily composed of metals, similar to the composition of meteorites that fall to Earth. But later, scientists discovered that the presence or absence of a dark absorption line depends on the ionization level of the atom. At that point, one or more electrons are ejected from the atom. This means that not all the elements present appear in the absorption spectrum. After decades of laboratory research to understand the effects of ionization, scientists have determined the precise ratios of the most common elements in the universe. 74% hydrogen, 24% helium, and 2% other chemical elements. However, this ratio has not always remained constant since the Big Bang. Stars are essentially giant chemical factories, continuously transforming lighter atoms in the universe into heavier chemical elements. This seemingly terrifying phenomenon is actually nuclear fusion, occurring in the extremely hot cores of all stars, where temperatures reach millions of degrees. At the beginning of the 20th century, French physicist James Baptiste Baron proposed the idea that helium is involved in the process of nuclear fusion on the Sun. But it wasn't until 1938 that scientists truly understood this mechanism. At the Sun's core, temperatures can reach 15 million degrees Celsius, and the gas is compressed to about 150 times the density of water. The heteronucleus is synthesized into a helium nucleus, releasing an enormous amount of heat. The 4 heteronuclear cores are essentially 4 protons transformed into a helium nucleus, where 2 protons and 2 neutrons are tightly bound together. But even at the Sun's extremely dense core, the simultaneous collision of 4 nuclei remains an extremely rare occurrence. Instead, a helium nucleus will be formed following the correct sequence of steps. In this process, 2 out of the 4 protons will transform into neutrons, with the lost mass converting into energy and being released as the Sun's light and heat. Inside the Sun's core, approximately 4 million tons of matter are converted into energy every second. This amount of material is enough to build more than 10 of New York City's famous Empire State Buildings. This energy source escapes outward and takes hundreds of millions of years to reach the surface, where the temperature is only about 6,000 degrees and the material density is 0.1% of the air density at sea level on Earth. From here, the energy is released into space in the form of electromagnetic radiation. If directed toward Earth, it takes only 8 minutes to reach our sky. It's fascinating to know that the warm sunlight shining on our faces today was actually formed in the Sun. Understanding the process by which stars create heavier elements through nuclear fusion is far from simple. And how does this process alter the structure of the star, since all those transformations remain hidden deep within its core? Only when a star is about to fade does it reveal its innermost self for the universe to behold, and on the ground, astronomers, ever vigilant by their telescopes, never miss that moment. Generally, stars die in one of 2 ways, depending on the amount of matter they possess. The first case occurs with stars of small mass, less than 8 times the mass of the Sun. Like all stars, energy is only generated in the core. As more hydrogen in the core fuses into helium, this process gradually weakens. Although the outer layers of the star contain more than half of its mass, this material still cannot penetrate the core to replenish the gradually depleting reserve. As the hydrogen burning process in the star's core slows down, the released energy also decreases, causing the star to begin contracting. This process raises the temperature and triggers hydrogen fusion reactions in the shell surrounding the gradually shrinking core. This shell will release a vast new source of energy, generating a powerful thrust on the star's upper layers and causing the outermost layer, originally about 1 million kilometers in diameter, to expand to hundreds of millions of kilometers. The outer layers gradually expand, turning the star into a red giant. If this phenomenon occurs with the Sun, within the next 5 billion years, it will engulf Mercury, Venus, and Earth. Inside the red giant's core, the heart continues to shrink and heat up. When the temperature reaches 100 million degrees with a material density 1,000 times that of water. When the temperature is high enough, helium begins fusing carbon and oxygen. This process lasts from 10 to 100 million years until helium exhausts its fuel and the star contracts again. The hydrogen fusion process around the core continues to expand, releasing an immense amount of energy that pushes the outer layers outward, until they are ultimately blown into space, forming a brilliantly glowing gas nebula. Planetary nebulae. As this dying star emits more layers of material, astronomers have a better chance to observe its core up close. Spectroscopic studies of planetary nebulae have confirmed the abundant presence of heavy elements. But most remain trapped within the stellar core, the heart of the nebula. When the outer layers of material are blown into space, the exposed stellar core appears as an extremely compressed gas sphere, roughly the size of Earth but 200,000 times denser and with temperatures reaching about 500,000 degrees. These are the white dwarfs that astronomers use to determine the age of the Milky Way. These stars are primarily composed of pure carbon and oxygen, along with small amounts of other chemical elements. Conversely, the second scenario occurs with stars that have a mass at least 8 times greater than the Sun. Stars with greater mass will generate significantly higher core temperatures after hydrogen fusion. High temperatures enable stars to form heavier chemical elements. Through the process of synthesis and acceleration, they continuously expand to an enormous scale. If by some miracle, one of these red supergiant stars could replace our Sun, it will fly to Jupiter. These stars have far more dramatic and extraordinary destinies compared to their smaller siblings. Red supergiant stars also undergo a similar evolutionary process as red giant stars, from their formation stage until the onset of helium fusion. Then, as the additional mass exerted intense pressure on the core, the star underwent further new bursts of burning and produce increasingly heavier chemical elements. The star will develop with a multi-layered structure stacked like an onion, enveloping the central core. Each layer will undergo a distinct nuclear fusion reaction. From the outside inward, the fusion process occurs in the following sequence. Hydrogen transforms into helium. Then helium further transforms into carbon and oxygen. The carbon in OCI transforms into neon and magnesium. Then the neon and magnesium further convert into silicon and sulfur. In the core of a mature red supergiant star, silicon and sulfur transform into iron and nickel. This is the sign foretelling the star's decline. All other fusion processes in stars release energy, but to synthesize iron and nickel, energy must be supplied to activate the reaction. The energy generated inside the star escapes outward, moving toward regions of lower density, much like water flowing downhill. Thus, the core will gradually deplete the energy needed to produce iron and nickel. The process of generating additional energy will cease. According to computer simulations, it takes only 24 hours to form an iron and nickel core with a mass twice that of the Sun. Once this mass is reached, gravity overcomes the repulsive force between atoms, making them inseparable. And the core rapidly contracted, forming a tightly packed heat sphere with a diameter of only 10 to 20 kilometers. After being compressed, the overlying layers of matter collapse into the core, triggering a violent explosion known as a Type II supernova. The energy released from a supernova generates an enormous nuclear reaction explosion, synthesizing chemical elements heavier than iron and nickel, including radioactive elements. When the explosion occurred, the newly formed elements were ejected and scattered into the cosmic void. When studying the remnants of supernovae that persist to this day, astronomers discovered that some of them are still expanding at speeds of up to thousands of kilometers per second. The gases emit light with distinctive colors even after the initial energy from the explosion has been depleted, as the radioactive elements within them decay and provide additional energy to sustain the excited state of the gas. Finally, the debris from planetary nebulae and supernova remnants will merge into the interstellar space, which is filled with gas and dust. Here, they will become the raw materials for forming new stars. Here is the English translation, choosing the first, more formal option. Where do stars come from? And so, each new generation of stars is born with more heavy elements than the previous one. Although these elements make up only